Okay, let's unpack this because I think it's something we all do without even realizing it.
Oh, absolutely.
Think about what happens when you wake up in the morning. You open your eyes and like instantly, effortlessly, you just see.
Right, there's no conscious effort at all.
Exactly. You don't have to consciously calculate the geometric distance to your alarm clock or, analyze the ambient lighting conditions
Uh-huh.
to figure out that the blurry shape on the floor is your dog and not a pile of laundry.
You just instinctively know.
Right. We take the sheer computational power of our eyesight completely for granted. But getting a machine, a computer,
Yeah.
to do that,
A whole different ballgame.
to get a machine to open a digital eye and actually comprehend the three-dimensional scene in front of it, it turns out that is one of the most complex, mind-bending puzzles in the entire history of engineering.
It really is.
Yeah.
Because computer vision isn't just about taking a digital photograph.
Right.
A digital photo is just raw data. I mean, it's just a flat, two-dimensional grid of millions of pixels.
And the computer doesn't naturally know what those pixels actually represent, right?
Exactly. To a computer, it's just numbers. Computer vision is the extraction of high-dimensional data from the real world to produce, well, numerical or symbolic information.
So giving it actual meaning.
Precisely. It is essentially the process of turning a chaotic flood of light, shadow, and geometry into a series of autonomous, logical decisions. We are teaching machines not just to record the world, but to genuinely understand it.
And today we are decoding that exact translation. We're doing a deep dive into a massive stack of documentation, pulling from decades of computer science history, hardware specs, and algorithmic breakdowns to really explore the mechanics of computer vision.
There's a lot to cover.
There really is. And for you listening, whether you're unlocking your phone with your face or driving past an autonomous vehicle on the highway, or even just buying produce that's been optically inspected on a conveyor belt, this deep dive is your cheat sheet.
Yeah, it's everywhere now.
We are ripping the lid off the invisible technological eyes that are constantly inspecting, navigating, and shaping your daily life.
And, to really grasp how sophisticated this technology is today, we have to look back at how completely we misunderstood the challenge in the first place.
Oh man, the hubris of the 1960s.
It's hilarious in hindsight. The pioneer scientists of artificial intelligence back then just assumed that vision was the easy part of intelligence.
Yeah, back in 1966 at MIT, the AI lab famously assigned computer vision to an undergraduate student as a summer project.
Just a quick summer gig.
They literally thought they could attach a camera to a computer and in a few months just write a program that would have the machine describe what it saw.
They fell into a classic cognitive trap, really.
How so?
Well, because human vision operates subconsciously, right? You don't feel your brain sweating when you look at a coffee mug.
Right, it just happens.
Yeah, so they assumed the computational load was incredibly light. They thought the hard part of AI was the reasoning, playing chess, solving complex math theorems.
So they figured perception, just translating a flat picture into a list of 3D objects, would be a simple stepping stone.
Exactly.
It's as if we thought teaching a computer to see was like teaching it to read a thermometer, but it turned out to be like teaching it to understand poetry.
That is the perfect way to frame it. And because it was like poetry, that one summer project stretched into decades of grueling incremental research.
Just trying to get the basics down.
Yeah. Through the 1970s, researchers realized they had to start with the absolute mathematical basics. They couldn't just say, hey, find the chair.
Right, because the computer doesn't know what a chair is.
Exactly. They had to write algorithms strictly focused on extracting edges, just looking for where light pixels suddenly turned into dark pixels.
Just to try and label lines and infer basic 3D structures from 2D blocks.
Right. And then the 1980s arrive, and the field gets flooded with these intense mathematical models to handle lighting and depth.
Yeah, things with great names like scale space, which was a mathematical framework for allowing computers to recognize an object, whether it was 2 feet away or 20 feet away, or contour models, which were known as snakes.
I love that name.
Snakes are a great example of this era's logic, actually.
How so?
An active contour model, or a snake, is essentially a digital rubber band. You drop it onto an image, and the algorithm shrinks that rubber band inward.
Until it hits something.
Right, until it hits an area of high gradient. A sharp change in contrast, which usually signifies the edge of an object. The rubber band wraps around that shape, helping the computer trace a distinct boundary.
That's so clever. And it wasn't just finding edges, right? By the 1990s, the field of computer vision started colliding with computer graphics.
Yes, big time.
They adopted a concept called bundle adjustment, which comes from photogrammetry. And photogrammetry is basically the science of making 3D measurements from 2D photographs.
So like if a camera moves through a room taking pictures, bundle adjustment is the incredibly heavy math used to triangulate all those different viewing angles to simultaneously estimate both the 3D shape of the room and the exact path the camera took.
It was a slow, mathematical grind of geometry and physics for decades. But then we hit the modern era.
The boom.
The boom. The entire landscape shifted violently with the explosion of deep learning and convolutional neural networks, or CNNs.
The famous CNNs.
Yeah. Instead of humans hand-coding what an edge or shadow looks like, we just started feeding millions of images into these networks.
So it learns on its own.
Exactly. A convolution is basically a sliding mathematical filter. The network slides this filter over the pixels of an image layer by layer, automatically learning to detect edges, then textures, then shapes, and finally, whole objects.
And it worked really well.
Unbelievably well.
Yeah.
Within a few years, these CNNs were surpassing human benchmarks on massive datasets like ImageNet, which contains millions of images sorted into thousands of object classes.
Okay, I want to push back a little on this idea of modern AI surpassing humans or having vision completely solved.
Fair enough.
CNNs are incredibly powerful, but there's this fascinating contradiction in the technology that came up in the source material.
Yeah, the dog breeds versus the filters.
Yes. On one hand, a CNN can easily classify a dozen fine-grained dog breeds or like specific species of birds with a level of accuracy that you or I would totally fail at.
Oh, I wouldn't even know where to start with bird species.
Right. But on the other hand, feed that same supercomputer an image with a modern digital camera filter, like a basic Instagram color tint, and it gets completely confused.
It totally breaks down.
Or it will fail to detect tiny, obvious details, like a small ant crawling on the stem of a flower or a person holding a thin quill in their hand. Humans never get tripped up by a color filter.
What's fascinating here is why that paradox exists. You and I don't just see with our eyes. We see with our entire life experience.
Oh, that's a good point.
We have massive amounts of contextual, organic knowledge about how the world operates. If you see a photo tinted a slightly purple, your brain instantly knows it's a lighting effect or a filter, and you just discount it.
You don't suddenly think the dog is a different species.
Exactly. And if you see a hand positioned with the fingers pinched together hovering over a piece of paper, your brain actively expects to see a pen or a quill, so you spot it immediately.
Even if it's super thin or blurry. Because computers don't have that organic context. They aren't expecting anything.
Precisely. They are disentangling symbolic information using models built entirely on geometry and statistics.
So it's all just math.
All math. When a digital filter subtly distorts the numerical pixel values across an entire image, the statistical model breaks down. The computer doesn't conceptually know what a filter is.
It just sees bad numbers.
Exactly. It only knows that the mathematical patterns it relies on to identify a dog have suddenly vanished into statistical noise.
Which really points to the massive gap between humans and machines. The reason computers get confused by a simple filter is that they don't have biological eyes or biological brains.
Right.
To fix that, engineers had to figure out how to build an artificial eye and brain from scratch. And that requires a literal Frankenstein recipe of scientific fields. Here's where it gets really interesting, though, because you literally need quantum mechanics just to snap a digital picture properly.
I know, it sounds like an exaggeration, but it is absolute reality.
It blew my mind.
Most computer vision systems rely on solid-state image sensors, typically CMOS sensors, that detect electromagnetic radiation. And to design those sensors, you need a deep understanding of solid-state physics.
Wait, hold on. Quantum mechanics. Just to take a digital picture?
Yeah.
I thought cameras were just capturing bouncing light through a glass lens. Where does the quantum realm actually come into play here?
It happens the moment the light hits the digital sensor. When photons of light travel through the camera lens, they strike a grid of silicon pixels. Because of the photoelectric effect, which is a quantum mechanical phenomenon, those photons knock electrons loose within the silicon.
So the light is physically freeing electrons.
Exactly. The sensor collects these freed electrons in microscopic wells, and the number of electrons in each well tells the computer exactly how bright the light was at that specific pixel.
That is wild.
You literally cannot engineer a modern, high-definition camera sensor without relying on the quantum interactions between light and matter.
Okay, so quantum physics gives us the raw hardware, the artificial eye. But what about the brain? How do we get the software to interpret those electron wells?
That's where we turn to biology.
Right. Over the last century, scientists extensively studied neurobiology, like human eyes, neurons, and the visual cortex, just to create a blueprint for machines. And there is a massive historical anchor from the 1970s, Kunihiko Fukushima's neocognitron.
A legendary piece of work.
Yeah, it was an early neural network directly inspired by biological vision, specifically how simple and complex cells in an animal's visual cortex respond to lines of light at specific angles. But if we are literally trying to copy the human brain, are we just building a digital clone of a human, or is a computer vision system doing something fundamentally different?
It is doing something fundamentally different. Neurobiology provides the architectural inspiration, but the execution is purely mathematical.
So it's not a true brain.
Not at all. Biology relies on physiological processes, like chemical synapses between living neurons. Computer vision relies on nodes with mathematical weight associations.
Can you give an example?
Sure. Let's look at how a network learns to recognize textures. Imagine training a network to recognize various sea creatures.
Okay, like a starfish.
Yeah, the starfish might strongly activate visual feature nodes for a ringed texture and a star outline. Meanwhile, sea urchins might strongly activate nodes for a striped texture and an oval shape.
But nature isn't always that clean. What happens if you feed the system an image of a rare sea urchin that actually has a ringed texture instead of stripes?
Well, the network adjusts the math. It creates a weakly weighted association between the urchin category and the ringed texture node.
Oh, I see.
So the next time it sees an image, it isn't just checking off a rigid list of features. It is calculating massive matrices of associated mathematical weight patterns across millions of nodes simultaneously.
Biology gave us the blueprint of a layered network, but the computer executes this through linear algebra and multidimensional signal processing.
Exactly.
So we have physical sensors designed with quantum mechanics and algorithms inspired by neurobiology, but executed through heavy math. How does a computer actually process a live scene in real time?
It follows a very strict pipeline.
Right. Let's walk through the actual assembly line of artificial perception.
The typical pipeline of a computer vision system is incredibly structured. It almost always starts with image acquisition.
Getting the raw data.
Right. And this isn't just snapping a 2D photo. This could be gathering 3D volume scans from a medical device or pulling sonic data from radar and ultrasonic cameras.
And you can't just feed that raw data straight into the brain, right? It has to go through pre-processing.
That can be cleaned.
Yeah. The system has to clean the data, reducing noise, enhancing the contrast, or resampling the image so the coordinate system is perfectly aligned.
And from there, you move into feature extraction.
And this is where it gets really granular. It's less like looking at a whole picture and more like looking through a tiny microscopic straw.
That's a great analogy.
The computer slides that straw across an image, and it is completely blind to what the object actually is. Yeah. It only notices when the pixels inside that straw suddenly shift from light to dark, or when a mathematical gradient spikes.
And that sudden drop-off, the computer logs that as an edge or a corner.
Exactly. And once it has mapped all those edges and corners, the pipeline moves to detection and segmentation.
Putting the pieces together.
The system decides which of those extracted regions are actually relevant. It segments the image, mathematically isolating the foreground object from the background noise. Finally, it moves to high-level processing and decision-making.
Right, like, is this segmented shape a car drifting into my lane?
Or does this manufactured circuit board pass quality inspection? It's like preparing a gourmet meal. Acquisition is buying the groceries, pre-processing is washing the vegetables, feature extraction is chopping them into exact shapes, and decision-making is the final taste test.
I love that.
But what happens when the groceries are spoiled? Say the camera lens is smudged, or there's heavy motion blur from a car moving fast, or bad lighting introduces a ton of static to the image.
It happens all the time in the real world.
A human can squint and still figure out what they're looking at. Does the computer just throw the degraded image away and give up?
If we connect this to the bigger picture, it makes sense how they handle it. This is where a subfield called image restoration becomes absolutely critical.
So they fix it.
Yeah, computers don't just discard degraded data, they actively reconstruct it. They use highly sophisticated local structural models to separate the noise from the actual signal.
How's that work?
Take a median filter, for example. If you have a corrupted pixel, say it's glaringly bright white because of sensor noise, the algorithm looks at a 3x3 grid of the surrounding pixels.
Just a tiny neighborhood around the bad one.
Right. It takes all 9 of those numerical values, lines them up, and finds the exact median value.
Oh.
It throws out the extreme white noise and replaces the corrupted pixel with that median number, instantly smoothing out the image without blurring the real edges.
It's literally guessing what should be there based on the neighborhood.
Yes. They even use techniques called in-painting to fill in entirely missing parts of an image.
Just making up missing data.
Kind of.
Yeah.
If there is transmission interference or severe motion blur, the system analyzes the existing local image structures, the lines and edges that are still visible, and uses multidimensional math to control the filtering process and rebuild the image to what it was intended to be.
To manage this entire assembly line, the system relies on image understanding systems, or IUS.
Right.
This framework breaks perception into 3 levels of abstraction. The low level is just the raw primitives, those edges and textures we talked about. The intermediate level builds those primitives into continuous boundaries, surfaces, and 3D volumes.
Getting closer to a real object.
Yeah, and the high level is where the math finally clicks into a semantic concept, an object, a scene, or a specific event.
And we cannot ignore the physical hardware required to run this intensely heavy pipeline.
Oh, absolutely.
Traditional CPUs simply cannot handle the sheer volume of parallel math required to calculate millions of pixel values 60 times a second. We are now seeing dedicated vision processing units, or VPUs, integrated directly into devices.
So we've built this insanely complex, noise-filtering, quantum-powered, biologically inspired deep learning pipeline.
That's a mouthful.
Right. So what is it actually doing out there in the world right now? Because the sheer scale of its application is staggering.
The market sizes alone tell the story of its dominance. In 2024, the leading sector for computer vision was industrial machine vision, with a market size of $5.22 billion US dollars.
Wow.
The medical sector reached $2.6 billion, and military applications were nearly $1 billion.
The specific use cases are where it gets truly wild. Take agriculture.
Oh, yeah.
There is an open source vision transformer model out there right now that farmers use to monitor their fields. It automatically analyzes the visual data of crops and detects diseases on strawberry plants with a 98.4% accuracy rate.
That is incredible.
It is literally securing food supply chains.
Or look at industrial manufacturing. They deploy high-speed vision processing setups that can track thousands of frames per second.
Thousands.
Yes. They are inspecting speeding glass bottles on a production line, instantly flagging microscopic cracks. They use it to check silicon wafers, the foundational pieces of our computer chips, for defects that are entirely invisible to the human eye.
That's wild.
They even use optical sorting to automatically blast undesirable foodstuff off of bulk conveyor belts using targeted jets of air.
Then you have autonomous vehicles. And I'm not just talking about the driver assist features in your car. I'm talking about space exploration.
World vision.
Yes. NASA's Curiosity rover and the Chinese space agency's U-22 rover use computer vision algorithms for SLAM. That's simultaneous localization and mapping.
Right.
They ingest camera data to simultaneously build a 3D map of the Martian or lunar surface while pinpointing their exact location within that map.
It's vital for navigation.
Or unmanned aerial vehicles, UAVs, flying high over dense forests, analyzing visual spectrums to detect the earliest thermal signs of wildfires before human towers can spot them.
But perhaps the most mind-bending application emerging right now is how computer vision is being used for tactile feedback.
Yes. This part completely broke my brain. The idea that vision is being used to create the sensation of touch.
It's brilliant.
Engineers are now embedding rubber artificial skin layers with tiny strain gauges. You place this skin over a robotic finger, trace a surface, and the computer measures the upward push on tiny rubber pins to map microundulations. But the far crazier version of this is the silicon domes.
Right. Engineers take a tiny high-definition camera and suspend it inside a flexible, translucent silicon dome like a robotic fingertip.
Okay.
They embed a grid of equally spaced point markers on the inside of that silicon. When that robotic fingertip presses against an object, the silicon physically deforms.
So the camera's watching from the inside.
Exactly. The internal camera watches how those point markers shift, stretch, and distort. The computer then uses that visual data to calculate the exact geometric pressure being applied to the mold.
It is using a camera to watch the inside of its own skin deform, which lets the robotic hand essentially feel the shape and firmness of whatever it's grasping.
It's incredible.
So what does this all mean? I have to push back on our core premise here. We call this whole field computer vision. But if a camera suspended inside a silicon dome is being used to help a robot feel a surface, Hasn't vision just crossed over into a completely different sensory category?
This raises an important question, though, about the fundamental trajectory of the technology. Machine vision is rapidly converging with robotics and visual computing.
So it's merging.
It is evolving away from a replication of human eyesight and turning into a generalized environmental awareness. The algorithms don't actually care if the input data represents visible light, physical pressure, or radar waves. It just processes high-dimensional data into autonomous decisions.
Just numbers to them.
Exactly. You see this vividly in modern military applications. The latest missile guidance systems don't just lock onto a pre-programmed set of coordinates.
They don't.
No, they're launched into a general theater of operation, and then they use locally acquired image data to actively deliberate and select their targets upon arrival. Vision has become synonymous with autonomous thinking.
That is both awe-inspiring and, frankly, terrifying. It really highlights the incredible trajectory we've unpacked today.
We've come a long way from a summer project.
We really have. We started with a naive undergraduate summer project in 1966, thinking a computer could just look at a camera feed and print out the list of objects. And today we have a multi-billion-dollar global infrastructure. We're leveraging the quantum mechanics of the photoelectric effect and the biological blueprints of the visual cortex to spot 6 strawberries, to navigate rovers across the Martian landscape, and to give robotic hands the physical ability to feel.
And if there's one lingering thought I'd leave you with, it's this. Computer vision is no longer limited to the visible light spectrum.
What do you mean?
Well, these processing pipelines are ingesting multidimensional data from medical CT scanners, hyperspectral imagers, and ground-penetrating radar.
Oh, wow.
They are quite literally seeing in wavelengths and dimensions that the biological human eye cannot physically comprehend. We have spent 60 years trying to teach machines to mimic our limited understanding of the world.
Right.
But are we rapidly approaching a point where machines won't just mimic us, but will eventually uncover, map, and act upon a version of reality that is completely invisible to us?
Wow. A reality right in front of us that we just don't have the hardware to perceive. It brings us right back to that alarm clock in the morning.
Exactly.
We open our eyes, and we naturally assume the world we see is the only world that exists. We take the puzzle of perception completely for granted. But the machines,
They're seeing much more.
they are just opening their eyes. And what they are starting to see is vastly bigger than we ever imagined. Thanks for joining us on this journey. Keep questioning what you see, and we'll catch you on the next deep dive.